All right, our next speaker is Brian McDonald from University of Rochester, who will speak on cycles and distance graphs in FQD. Oh, please go ahead.
All right, and thank you very much to Professor Nathanson for inviting me to speak. And yeah, this was joint work with Alex Yosevich, who's my advisor at University of Rochester, as well as Gail Jardine, who is another one of his graduate students. And yeah, we're estimating the number of cycles of an arbitrary length in distance graphs on FQD. Yeah, so when Q is a power of a prime, so let FQ be the finite field with Q elements, so that FQD is the d-dimensional vector space over that field. And we're going to be taking the dimension to be at least 2. So for 2 points in this space, our notion of distance is going to be algebraically analogous to the Euclidean case, except we're not taking a square root because not everything in the field has a square root. So when you fix a subset of this vector space and a non-zero element of the field, we can look at the distance graph on that set. So the vertex set is your set E, and we're going to have an edge between 2 elements of E when the distance between them is equal to T. And then we can also define something analogous for dot products, where once again, you take your vertex set to be E, and you put an edge between 2 points when their dot product is equal to T. So those are the objects we're going to be looking at. And then some of the tools that are going to come up are Fourier analysis on finite fields. So if chi is a non-trivial additive character of your finite field, then this is how you define the Fourier transform, which is analogous to the Euclidean version. And then with it defined this way, again, similarly to the Euclidean version, we have formulas for Plancherel and for Fourier inversion. And the proofs of these things are essentially the same as in the Euclidean case. So what is known previously about distance graphs on FQD? Quite a lot. So going back to 2007, Yosevich and Rudnev counted the number of edges on this graph. And okay, so we're getting the size of E squared over Q. And whenever I have a set with bars around it, that's going to be the number of elements in that set, which throughout the talk is going to be finite. They're all going to be finite sets. So this is the main term, and the error term is at most 2 times Q to the D minus 1 over 2 times the size of E. So the way the arithmetic works out, if the size of E is at least 4 times Q to the D plus 1 over 2, then they're going to be at least 1/2 size of E squared over Q edges, right? So in that case, the error term is no more than half the main term. And of course, as the size of E gets bigger, the error term gets smaller. So there's also a year later from Hart and Yosevich, we have an analogous result for the dot product case. So once again, we're counting the edges on the dot product graph in this case. And sort of heuristically, right, this main term is what we should expect because the number of pairs of points in E is the size of E squared. And if you pick an arbitrary pair of points in FQD at random, then you have a probability of 1 over Q that they have distance T. Okay, so these are sort of heuristically what we would expect anyway. So where else can we go with this? What else can we do besides counting the number of edges? So one thing we could do is look for the number of isomorphic copies of a given graph G that shows up in either the distance graph or the dot product graph on E. So, okay, here's one result in that direction. This is from Bennett, Chapman, Covert, Hart, Yosevich, and Pakianathan from 2016. So this is the case where your graph G is a path of length K, right? So we have a sequence of K plus 1 vertices where there's an edge from one to the next one. And so this is the result we get. If E is bigger than a constant depending on K times Q to the D plus 1 over 2, then there are approximately the size of e to the k plus 1 over q to the k edge preserving maps from G into the distance graph. So when we write it this way, where we're talking about edge preserving maps, right, then we're not actually looking at the number of isomorphic copies of the graph G, because there could be degeneracies in the sense of repeated vertices. But for this result, that's fine. And then here's a result that actually is counting, that actually is looking for isomorphic copies of the graph G. So this result would not include degeneracies in the sense of having repeated vertices. But yeah, so one thing to note in the first of these theorems is that the exponent d plus 1 over 2 is in some sense sharp. Like it would be sharp without additional hypotheses as a result of Yosevich, Ko, Rudnev, and Hart constructed some examples that show that even when you're just, that showed that there are sets on the order of q to the d plus 1 over 2 that don't actually have every possible distance. So that would, yeah, sort of a firm barrier here. But yeah, for the second result, Yosevich partial, so this is more general, right? We're looking at just any graph G. It doesn't have to be a path. At the expense of the exponent is a little worse than in the other one. So if we're looking at a path, then the maximum vertex degree would be 2. So that would be the case t equals 2, which would give us an exponent of d plus 3 over 2. So that's a little bit worse than the other one. Another example to point out is, let's say that G is a complete graph on n vertices. In that case, t equals n minus 1. And so then this gives a meaningful result in once D passes the threshold of 2n minus 3. Okay. Okay. So, right, and as I kind of mentioned, there's a heuristic principle that so far all the examples that we've looked at have obeyed, right? Is that if we're counting the number of copies of the graph G with n vertices and k edges in either the distance or dot product graph for large sets, then one expects to find roughly size of e to the n over q to the k copies of G. And once again, this is because size of e to the n, that's how many n tuples of points in E you have. And for each edge, you have a probability of 1 over q of having the right distance if you choose them randomly. Now, once again, for small sets, there's no reason to expect something like this to happen. But yeah, for large sets, this is the heuristic. And this agrees with the previous results we have. This heuristic is not always true, right? It's not a theorem. And one good counterexample is that there don't exist any equilateral triangles of length 1 in P2 when P is 5 or 7 mod 12. And the reason for that is that the square root of 3 is not in the field. And so you can see if you had such a triangle, you could translate it so that one of the vertices is at the origin, and you could rotate it so that one of the other vertices is on the x-axis, and then you would get a contradiction by thinking about what the coordinates of the third vertex are. Right. So what are our main results? So let Cn, and there could be two versions depending on if we're talking about the distance or the dot product case, but let Cn be the number of cycles of length n in the distance or dot product graph. Right, so by cycle, we just mean a sequence of vertices where xi connects to xi plus 1, and then it wraps around xn connects to x1. And right, so these are possibly degenerate cycles. These ones, we would allow repeated vertices when we're counting these. And then if we want to specify the non-degenerate ones without repeated vertices, we'll use n sub n. And a lot of the results that we have are going to be true, whether we're talking about the distance or the dot product case. The techniques are actually a bit different, but a lot of the results are going to be true for both. So we may omit the superscripts. Okay, so here's one of our main results. So this is counting the number of cycles possibly degenerate. So here the threshold on the size of E that we have is this. So when you look at this exponent, one good thing to compare it to is d plus 1 over 2, right? Because that's what in some settings we think of as optimal. And you'll notice that when k gets large, this gets as close as you like to d plus 1 over 2. And for small k, it's a little worse, but it's never any worse than d plus 2 over 2. Yeah. And this is kind of an artifact of the way that our proof worked, but we don't necessarily think that it actually should be worse for smaller values of k. All right, so what is k, right? So here we have a cycle of length n. So if it's an even length, then n is 2k, and if it's an odd length, then n is 2k plus 1. Yeah, so and so under this hypothesis, right, if the size of E is big enough, what do we get out of it? We get that the main term is this, size of E to the n over q to the n, which again agrees with our heuristic. And the error term is right, as q gets large, this is much smaller than the main term. Okay, so that's the result for possibly degenerate cycles. If we're specifying non-degenerate cycles, we have a very similar looking result. So under the same hypotheses, meaning the same restriction on the size of E and n is still at least 4. Under the same hypotheses, we get the same main term, but with a slightly worse error term. And you'll see that this first part of the error term is actually the error term from the previous slide. And the way this works out is, in order to count the non-degenerate cycles, we're going to count all the cycles, including possibly the degenerate ones. And then we're also going to find an upper bound for the number of degenerate cycles. And that upper bound for the number of degenerate cycles is where these terms come from. Yeah, and you'll see that this epsilon here is related to what the exponent was in the restriction on the size of E. Okay, so right, and in order to get the result for non-degenerate cycles, we actually had to get a result for trees as well. And yeah, so I'll say a bit more later about how that applies to the non-degenerate cycles, but here's the tree result for now. So if you fix a tree with r plus 1 vertices, so it has r edges, for any epsilon greater than 0, if the size of E is at least q to the d plus 1 over 2 plus epsilon, then you can find some subset E prime where its complement has this bound, which essentially means that E prime is almost all of E as q gets large. So what's the result that we get out of this is that if nt is the number of edge preserving maps from your tree into the distance or dot product graph on E prime, then we get the main term that we would expect from our heuristic with an error term that is good enough for our results. Yeah, and once again, when we're phrasing it in terms of the number of edge preserving maps of T into this graph, then we are allowing for degeneracies here in the sense of repeated vertices. Okay, yeah, so but independently, yeah, as far as I know, there isn't a result that covers trees other than that Yosevich partial that I mentioned earlier, which would have a which had a worse exponent, but of course covered a lot more types of graphs. Okay, so how do we prove any of these things? So this was one of the main tools we had. This was also a theorem from our paper last year. And so, okay, so this sum here, right, this is what we're estimating, and what is it counting? So if we're going to look ahead a little bit, we're going to end up choosing f and g to be the number of paths from x to y of length k in the distance graph or dot product graph. and so if we think about what we're actually, right, okay, in this version, it actually is the distance graph, not the dot product graph. And so if we think about what this sum is counting, right, it's counting quadruples of points in E, X, Y, Z, W, or sorry, it's counting, right, so it would be for, so before we take the sum, for a fixed X, Y, Z, and W, this would be counting, sorry, as long as there's an edge from X to Z and an edge from W to Y, then this would count the number of, so if we have a path from X to Y of length K and a path from Z to W of length K, and we have X connected to Z by an edge and we have W connected to Y by an edge, then what this really is a cycle of length 2K plus 2. So when we sum over X, Y, Z, and W, what we're getting is the number of cycles of length 2K plus 2, which is what we're trying to estimate. And so we get, right, the main term involves the L1 norms of F and G. And here, when I write L1 and L2 norms, right, these are just the usual LP norms where we have the counting measure on FQD. Right, and so the error terms are bounded in terms of the L1 norm, the L2 norm of F and G, as well as the L2 norms of capital F, capital G, capital F prime, capital G prime, right, where capital F, for example, is you're summing over the Y coordinate in F. Okay, so how does this allow us to set up an induction? So as I just said, in order to estimate Cn, the number of cycles of length n, we end up having to bound these quantities, the L1 and L2 norms of little f and the L2 norm of capital F. And yes, there are other terms floating around like G and F prime and stuff like that, but by symmetry, these are really the ones where we have to understand what's going on. Right, so as before, f of x, y, this is the number of paths from x to y of length k in the distance graph. And so the L1 norm of that, right, because so f of x, y is the number of paths of length k with fixed endpoints. So when we sum over all possible pairs of endpoints, we're getting all possible paths of length k. But this is already known. This was one of the results I mentioned in the beginning. So in the distance case, this was already known by Bennett, Chapman, Covert, Hart, Yosevich, and Pakionathan. And then for the dot product version, we use the same method as in their paper to get the result for the dot product version, so that in both cases we can apply it here. As for the L2 norm of f, right, so if we square f of x, y, we're getting the number of pairs of paths from x to y. Well, a pair of paths from x to y is the same thing as a cycle where x and y are opposite points on that cycle. So once again, if we sum over possible pairs of points x and y, we're getting every possible cycle. Yeah, and so then there's a square root because it's an L2 norm. And so, right, what remains to estimate is the L2 norm of capital F. Okay, so, right, and once again, capital F was this. It was the sum over y of f of x, y. So this is the L2 norm squared. And so we have this sum squared, so we will duplicate the variable. And yeah, so since fxy is the number of paths of length k from x to y, f of xy times f of xy prime, this is the number of paths of length 2k, where x is the midpoint and y prime are the endpoints. So once again, since we're summing over x, y, and y prime, what we end up getting is every possible cycle of length 2k. Or sorry, every possible path of length 2k. Yeah, and once again, there's a square root because it's an L2 norm. So this is really what allows us to set up the induction, is that the numbers of paths we already understand well from the previous result and from adapting that method to the dot product case. So because we understand those well, then this allows us to set up an induction, at least for the even length cycles. The odd length cycles, it's the same thing basically. But yeah, the odd case is basically the same thing. You would just, instead of choosing f and g to both be paths of length k from x to y, you would choose f to be the paths of length k and g to be the paths of length k plus 1. And then you could do a similar thing. So yeah, so let me just sketch a proof of how we got an estimate for this sum, because that was really the starting point of this whole induction. So right, just to remind you what the theorem was, it's this. So I'm not going to go through all the details, but so let ST be the indicator function of the sphere of radius t. So we have this bound on the Fourier transform, and this comes down, so it can be reduced to a Kloosterman sum that I think quite a while ago. And so, right, so if we write the sum this way, and then we use Fourier inversion on ST, and then we use the definition of the Fourier transform of f and g along with some algebraic manipulation, and we get this. And so now, once we're at this point, the observation is that, so when we take the m and l equals 0 term, this gives what ends up being our main term. And then the other terms, we have to show that they're smaller. And then, yeah, so this here is the m and l equals 0 term. And then we know what the size of ST is, right? This is a sphere in a d-dimensional space. So it's a d-1 dimensional object. So it's roughly this size. So this is where we get our main term from. And I'm not going to go through the estimates of the error term, but yeah, they're in the paper. Yeah, so for the dot product case, you want to estimate the same sum, and we set it up quite similarly, except now, right, saying that the dot product of x and z is equal to t is not right. We can't write it in exactly the same way because there's not a function where that can be encoded as just a function of x minus z or something like that. But that's fine. So we'll write it this way, which it really is pretty similar to what we were doing in the other case, just written differently. Right. So as we sum over alpha and beta in FQ, what this is going to do is pick out exactly the x, z, w's, and y's that have the property where x dot z equals w dot y equals t. And then once again, we're going to pick out the terms where alpha and beta equals 0, and that gives us what ends up being our main term. And then we have to show that everything else is small. So that's the setup on that side. Okay, so how about the degenerate versus non-degenerate ones? So far, everything that we've done has allowed for degenerate cycles. We've allowed for repeated vertices with the entire argument that I've described so far. So now let's try to bound the number of degenerate cycles, so with repeated vertices. So if you have a cycle with k vertices and it's degenerate so that there's repeated vertices, then what that means is you have a graph with at most k minus 1 vertices. And it has a spanning tree, which then has the same number of vertices as that graph, right? Because it's a connected graph. Right, and so then we're going to use our result we had counting trees basically to find an upper bound for this. So we bound the number of trees with k minus 1 vertices, and we end up getting a bound for the number of degenerate cycles. And there's a lower bound for the number of non-degenerate cycles. Yeah, so what else is left that could be squeezed out of this method, right? So just to summarize what we have now, we have estimates for the number of paths and the number of cycles of a given length in the distance graph and the dot product graph on a subset of FQD. And we have an upper bound for trees. We didn't actually have an asymptotic estimate for trees, just an upper bound. So what else could be done, right? So we did cycles and paths. Is there something else, is there another way to set up the induction that gets a larger class of graphs? And probably, but the difficulty is sort of when you're doing those L2 estimates. Because the nice thing about looking at paths is that, right, when we were taking the L2 of paths, we get cycles. And if you're looking at more complicated graphs, the induction might not work out so nicely. Is there another general of our functional theorem that could help with this, right? So what our theorem was doing is essentially allowing you to glue two things to, like, take two graphs and glue them together by adding two more edges. Maybe there's a better setup or a more general thing that could be done. And then lastly, right, so we did this for distances and dot products. So one question is there a unifying framework where we could have the same argument for both cases? And could it be generalized to other functions that are not distance or dot product? Okay, so yeah, I'll see if there are any questions.
Thank you very much, Brian. Are there any questions? If not, thank you again. And our next talk